homomorphism. So what I wanted to say was the following. So suppose we have a map P from A1 to A2. Suppose this is a homomorphism of abelian varieties. So then we can lift it to a homomorphism of C to the power G1, where this is the dimension of the first one, to C to the power G2, where this is the dimension of the other one. And when we do it, so which is thus a linear map, and this allows us to, so from here you will be able to classify homomorphisms of abelian varieties. You just say that we're going to look at linear maps of their covers such as they are invariant in an appropriate fashion with respect to the fundamental group. And you can prove that for a very general abelian variety A, we have and the morphism group of A is just Z, and this is the maps Z goes to NZ for some integer numbers n. Okay, so this is a classification of entomorphisms of a very general abelian variety. Okay. Another question you can study is the Picard group of an abelian variety, and there was something that we discussed, that there is a sequence going from 0 to peak node and so on and so forth. Okay, so what I wanted to say was the following, that there is a relation between the endomorphism and the Picard group. But one thing I wanted to say is that the endomorphism of A cross A is not equal to Z, it's bigger. And this is somehow an example that will turn out to be useful, very useful for what follows. So in fact, let me construct for you an endomorphism, a homomorphism of A cross A to itself, which is not just multiplication by a number in Z. So example, so we can of course multiply points, but we can consider a map from A cross A for any abelian variety to A cross A given in the following way. You take xy, a pair xy, you take it to a pair x plus y and x minus y. This is certainly not the same as just multiplying by a number. I mean, explicitly not the same. And you can study its kernel. So let's call this maybe P. So the kernel of this P, what is it? It's the set of pairs xy such that x plus y is 0 is equal to x minus y. So what does this mean? So from here it follows that x must be equal to y and 2x must be equal to 0. So what does this mean? What does it mean to have 2x equal to 0 on an abelian variety? This means that the kernel of P is a set of points x comma x, where x is in A2. So this is my notation for points of order 2. So this is the kernel of the map 2 going from A to A, which takes Z to 2Z. Okay. The number of such points can be computed. The number of points of order 2 on an abelian variety is computable, and this is 2 to the power 2g. So for example, for an elliptic curve, A tor, which is C quotient Z plus Z tor, the set of points of order 2 on this elliptic curve is, well, the point 0 is certainly a point of order 2. The point 1/2 is a point of order 2. 2 over 2 is of order 2, 1 plus 2 is of order 2. So if I were to draw the usual parallelogram picture, the points of order 2 will be this one, this one, this one, and this one. And in general, you can convince yourselves the number of points of order 2 is going to be 2 to the 2g. Okay? So we can have a definition, just for convenience. And isogeny is a homomorphism of is a surjective homomorphism, of abelian varieties with a finite kernel. Okay. So, for example, this is an isogeny, right? The kernel is a finite set of points, and it's certainly onto, because you can just construct x and y mapping to any point here. Okay. Actually, if you have two abelian varieties of the same dimension, they have a map of one to the other with a finite kernel, the image has to be the same dimension as the source, so it has to be onto. There is not much you can check. It's just a convenient word. And there is an isogeny theorem. There is an isogeny theorem that I won't state in full generality. It would require more terms and techniques than we need for the rest, describing the pullbacks of line bundles under isogenies. Okay. So I wanted, though, to state the result of this for one particular kind of isogeny, for this isogeny, because this will turn out to be very useful for what follows. For this, let me just introduce notation. A PPAV is a shorthand for a principally polarized abelian variety. And we'll write a PPAV as A comma theta, where this is the abelian variety and this is the principal polarization. So whenever I write A comma theta, I do mean a principally polarized abelian variety, so I mean this is a principal polarization. So it's an ample line bundle with a one-dimensional space of sections. So just convenient notations for me to avoid saying a principally polarized abelian variety with polarization L that I'll denote by theta. There is a historical reason why this is called theta, which will become apparent when we write down the theta function. Okay, so isogeny theorem for this example. So for the map P gives the following result. So if you have a product of two abelian varieties, how do you construct a line bundle on that? Well, you take a principal polarization on one, a principal polarization on the other, and you take their product. So what you can do is you can take the product of polarizations. So this is an exterior product of line bundles. So this means a line bundle on A cross A such that it is theta on the first factor on each factor, and also theta on the second factor. So when you have a product of two varieties and you have a line bundle on each, you can construct a line bundle on a product which transforms as this line bundle, and the first line bundle in the first direction and the second line bundle in the second direction. That's what I mean here. And this pullback, in fact, turns out to be equal to 2 theta times 2 theta. So this is an additive notation for the line bundle, which is the tensor square of the theta line bundle. Okay? And the isogeny theorem tells us something else, in fact. So here there is a unique section, and here there is a unique section. So this product will have a unique section, which if you said that there were coordinates, say x1 and x2 here, it will be like the theta of x1 times the theta of x2. So this thing will come with the natural section, the pullback of this section. And the isogeny theorem will actually describe the section that we get here in an appropriate basis, but we'll do this analytically. So that's one example I wanted to point out. And then you can ask, why on earth would this be of any interest? Why is this peculiar example more interesting than any other isogeny you could come up with? Well, the answer is, well, you are free to choose any isogeny you'd like. You'd get some identity here from the isogeny theorem. This seems to be somehow very useful for applications. Another kind of a very useful isogeny is an isogeny from the fourth power. Why am I skipping the third one? Because there is no sort of nice symmetric isogeny from the third power to itself. So another example will be, let's call this P4 maybe. This will be an isogeny of A cross A cross A cross A cross A to A cross A cross A cross A. And the reason that we do this is that there is no nice is just colloquial. I'm just trying to say that somehow not much use has been made of this. No nice useful isogeny of A cross A cross A, 3 copies to itself. Of course, you can construct many maps. As an endomorphism ring of A cross A cross A cross A is quite big. I mean, you can take the factors and essentially add them up any way you like. But there is somehow no nice symmetric way, and this is not so, hasn't been so useful. So the example here, the very useful example here will be x, y, z, t. So this is just a quadruple of points on the abelian variety. I'll have to tell you where it goes. And the formulas here will be x plus y plus z plus t, x plus y minus z minus t, x minus y minus z plus t, x minus y plus z minus t. So essentially, so on c to the power 4g have the linear map, the lifting of this, the linear map that lifts this is just given by the matrix 1, 1, 1, 1, 1, 1, 1, 1 minus 1 minus 1 minus 1 minus 1 minus 1. I should write it as a matrix if I started doing this. Right? So this is a matrix. And if you look at this map, you can study where its kernel is going to be. And it's again going to be essentially points of order 2 if you work out the details. And that's somehow useful. And the pullback of theta cross theta cross theta cross theta is going to be essentially theta cross theta cross theta cross theta. So this is a useful example. Okay? So this is just useful. I won't write down why, but it's another example to have in mind where studying such an isogeny produces useful information. Okay? So this is some information about isogenies. I should also say that for a generic abelian variety, so for a very general fact, for a very general principally polarized abelian variety A theta, it admits only one numerically line bundle, which is to say the Néron-Severi group of A is theta. So this is the Néron-Severi group. So this is line bundles up to numerical equivalence. Is equal to z theta. Okay, that's another useful fact to have in mind. So this means that for a very general abelian variety is in some sense very simple. The Néron-Severi group is very small. The endomorphism algebra is also very small. They're both z. And this somehow maybe will tell you that it's very easy to study a very general abelian variety. But actually, exactly the opposite is true. So difficulty with abelian varieties with very general principally polarized abelian varieties is the following. They have essentially no geometry. Because you see the Hodge diamond does not depend on A. Certainly. I mean, this is not even for general. The Picard of A is too simple. The endomorphism is algebra of A is too simple, and so on. Somehow there is no structure you have here. So if you wanted to study the geometry of Riemann surfaces of curves, you could start imposing conditions on certain sections of line bundles, their syzygies or whatnot. It doesn't work for abelian varieties, for very general abelian varieties, so way because there's not so much structure. For very general, for non-general, you know, different things could happen. Okay, so that's somehow what the abelian varieties are, and the object of study I wanted to define was the moduli space of abelian varieties. So let me define that. So first let me introduce notation. Let Hg, called the Siegel upper half space, be the set of G by G complex matrices. Can you see well up here? Is that okay? Which are symmetric and have a positive definite imaginary part. Okay. So why do we care about that? Is, well, given such a matrix, we can construct the corresponding abelian variety. But this is just notation for such a set. So let Ag, this is A, be the moduli space of G-dimensional principally polarized abelian varieties, complex, as everything principally polarized abelian varieties, up to by holomorphisms. So this means we consider the set of abelian varieties and declare them to be the same if they are isomorphic, right? So this is the moduli space. I'm not going to make any statements that any good algebraic geometer should make at this point about how well this is defined, whether this is a nice space, whether this is a stack, what the stabilizer is, and so on. So technically, I'm supposed to say this is a nice Deligne-Mumford stack with a stabilizer of order 2 for a general point, because there is a plus minus 1 involution on any abelian variety, but I don't want to say that. I said it, but let's not worry about it. I will have a much more analytic view of this soon, because we'll need to have the analytic view. So I don't want to worry about whether this exists as a nice space or whether this does not exist as a nice space. Okay. So we certainly have a map which takes the Siegel upper half space to the moduli space of abelian varieties, because you just take tau and you associate with the abelian variety corresponding to tau, which recall was the quotient of c to the g by z to the g plus z to the g times tau. Okay? So this is a map. And there is a fact, which is the following fact. So this describes what happens here. So the fact essentially describes what maps the abelian varieties have to themselves if you leave them to c to the g. So you have a map of an abelian. If you have an isomorphism of one abelian variety to the other, this leads to a linear map of c to the g to c to the g. And what this fact tells you is that the moduli space of principally polarized abelian varieties is actually a quotient of the Siegel upper half space by the symplectic group with integer coefficients. And you might be surprised as to why the symplectic group should enter here anywhere. But see, this is a moduli of principally polarized abelian varieties. So up to bi-holomorphism means respecting polarization. So this means your bi-holomorphism should map the polarization to the polarization and not somewhere else. And the polarization we discussed was essentially a pairing. It was an element of H11, which induced an odd bilinear form on the lattice. So somehow the symplectic group, this is the pairing on the lattice that you have to preserve. Where the action, I should probably write it down, where the action of the symplectic group on the Siegel upper half space is as follows. So if we have a gamma that I'll write in G by G block form, so this is an element of the symplectic group in G by G block form. And when I write it in G by G block form, this means that the symplectic metric, the symplectic form preserved is 0, 1, minus 1, 0 in G by G blocks. So this should remind you of the picture we had for a polarization some time ago. So this is a symplectic form, which is 0, 1, which is sort of the principal polarization. It has all ones along the diagonal. And I write a matrix as a G by G block form, preserving this thing. So it means if I conjugate this matrix by the element, it should be preserved. It should be itself. So ABCD times that times ABCD conjugate is itself. Okay? So the action is, if you take such a gamma and you want to act on tau, and you might argue that I should be acting on the right, not on the left, because I'm writing this as a right quotient, and you're right, and you should object, but I'll still write it this way. And because I'm probably making more than one mistake about left versus right here. So I think this should be C tau plus D inverse times A tau plus B. Okay? So tau again is a G by G matrix. A, B, C, D are all G by G matrices with integral coefficients. Tau is a matrix with complex coefficients. You can construct this. You can construct this. There is an implicit claim here that this matrix has to be inversible, essentially due to the fact that tau has a positive definite imaginary part. So the imaginary part of all of this will be like C times the imaginary part of tau, essentially, and so on. And this is the way it works. It's very common in the field to make a mistake as to whether you take a left or right quotient, of whether you multiply on the left or you multiply on the right, whether the lattice is z to the g times tau, or tau times z to the g, and so on. And depending on your convention of whether you write vectors as rows or columns, there is a correct way to do it. But of course, in my notes, I tried to do something. By the time I finished writing the notes, I realized I made a mistake somewhere. So let's not worry about it. I mean, there is a right way to decide where you act on the left, where you act on the right, and so on. But let's rough this idea. So the claim here is essentially the following. The claim is that if you take two matrices in the Siegel upper half space, so if you take two symmetric matrices with positive definite imaginary part, and look at the two corresponding abelian varieties, these two abelian varieties, principally polarized, will be biholomorphic if and only if one of them can be obtained from one of the matrices can be obtained from the other one by acting by the symplectic group. This is a point where you may be able to catch me, and you may ask me the following very good question. And the question is as follows. Given such a period matrix, here is the abelian variety. Where exactly is the polarization? Right? I'm talking about the moduli space of principally polarized abelian varieties. So, I mean, this somehow comes with a natural principal polarization. And this is something I was conveniently sweeping under the rug some of the time, but it is very important. So there is a natural way to endow this thing with a principal polarization. I'll write down a formula in 10-15 minutes for what happens here. But it's very important. You notice if you try to consider moduli of abelian varieties with no fixed principal polarization, You can, for example, shift the abelian variety. You can just take you can consider the map that takes the abelian variety and shifts it by a vector. And then you would not end up with a good moduli space because every point will have an infinite stabilizer. That's bad. Okay, you can skip this remark. It's not important for what's going to follow. Okay. So this is the definition of the moduli space of abelian varieties. You notice this is a discrete group. So you see that the dimension, the complex dimension of the moduli space for abelian varieties is the same as the complex dimension of the Ziegler-Laplace half space. And this is the dimension of the space of symmetric G by G matrices. So this has to be G times G plus 1 over 2. Okay? Just compute it. Okay. So that's one object of study. Okay. So this is the moduli space. I mean, I never properly constructed it, but you can think of this as a quotient. And then it's not so bad. So you just need to verify essentially that the stabilizer under this action of any point in the Ziegler-Laplace half space is finite and sort of bounded. Then it will become a nice orbifold, and we should be relatively safe. This was a comment meant for people who care about the stack theory. If you're not one of those, discard this comment. That's a nice moduli space. Okay. Properly called the moduli stack, but still a nice modulation. Okay, so as I said, a general abelian variety doesn't really have so much geometry. It's not very clear how to study it. So the question is, do principally polarized abelian varieties occur in nature? Are there any constructions where we get them? And yes, they do. So next thing is Jacobians of Riemann surfaces. And with apologies to algebraic geometers, I will be calling algebraic curves Riemann surfaces from now on, because there will be curves on Riemann surfaces at some point, and I don't want to say curve in a curve. Okay. So I probably should define this. So many of you may know different definitions. We're now doing the algebraic definition, so let's try to think about it. So let me define for a curve C of genus G for a Riemann surface C of genus G, we let the Jacobian of C be the group peak G minus 1 of C. So this means line bundles, and it's a line bundles on a curve, so there is a notion of degree. So this means line bundles of degree G minus 1 on the curve C. Okay, that's the definition. Okay. Now you can ask, why did I pick degree G minus 1? That's a good question. There'll be two answers in a second. So, but let's first study what happened if I chose some other number here. So there is a following fact that, remember, for an abelian variety, I had 0 went to peak node of A, went to peak of A, went to H11 with coefficients in Z. So in general, recall that for any x, we have 0 goes to peak node of x, so that goes to peak of x of arbitrary degree, goes to H11 x Z 0, right? Under certain assumptions that we won't worry about too much. So I won't write any x. I don't want to worry about singularities or anything like that. Okay, so in particular for curves, so we wrote this for abelian variety. This was a dual abelian variety, and this was our understanding of the Picard. So in particular for a curve C, we'll have 0, we'll go to peak node of C, we'll go to peak of C, we'll go to Z, we'll go to 0. Because you see, for a curve, H11 is just the same as H2. It's one-dimensional. It's one-dimensional space. Right. So what is this number Z? This map is just the degree of a line bundle. Right? So thus peak, n of C is isomorphic to peak node of C for any n, right? So peak n means bundles of degree n, but not canonically. So this means I could have written anything here. I would have gotten an isomorphic variety, but not a canonical isomorphic variety. For a long time I thought this was all nonsense, because if they are isomorphic, it doesn't really matter, it's not canonical. But there is something very important that I'd like to explain here, which somehow creates a little bit of a difficulty in many different places, and I want to explain what this is. So this is an abelian variety, I claim, right? But how do you add points here? So suppose you have 2 points on peak G minus 1. How on earth are you going to add them? Not so clear, right? So remark, if I were to choose peak node of C, it certainly is clearly a group, right? Because you just take two line bundles of degree 0, you take their tensor products, that's certainly a 0. And I mean trivial bundle, and 0 is a trivial bundle. Okay. Now on the other hand, I need to have a principal polarization, and I also have an involution at some point that I'll have to worry about in a second, because the abelian variety also has an involution x goes to minus x, which you can see here, it seems, right? I mean, it just takes the bundle to the inverse, but that's not such a good idea. So however, the choice of on peak G minus 1 of C, there is a natural polarization. So I'll just define this polarization by saying the theta is the set of all line bundles in the Jacobians, so in peak G minus 1 of C, such that they have sections. Okay. Well, why is that an interesting definition? I should probably convince you that this is actually a divisor theorem. Theta is a divisor in peak G minus 1 of C. And I realize it's an easy theorem, but I wanted to somehow demonstrate a little bit of how you work with such things. So I want to give an indication of a proof. But before that, are there any questions? So I give a formal definition of a Jacobian in this way. I then state that if I chose any other degree here, I would have an isomorphic variety, but I want to have this not just as a variety of a certain kind. I want to have this as a principally polarized abelian variety. At the moment, I only told you that it's very easy to see the additive structure, the group law on peak node, not on peak G minus 1. But I now want to convince you that peak G minus 1 is nice, because there is a notion of a very natural divisor on it, this thing, which you would not have on peak node. So proof, and please, for today and tomorrow, do take my proofs with a grain of salt. I mean, they're not necessarily complete. I'm not proving necessarily all the things that I'll need to prove, but I want to indicate how this happens. So what I want to compute is I want to compute H node of D for a generic D. And I'll then convince you that for a generic degree G minus 1 line bundle and a generic curve C, the H node will be exactly 0. The expected H node will be 0. And then by some general theory, it would somehow follow that the expected H node being 0 means that on codimension 1 it will jump to 1. And that's what I want. Okay? So the proof is as follows. So recall there is a Riemann-Roch theorem. On C, which is to say that for any divisor D on C, what we have is H node of D on C minus H node of KC minus D. So this is the line bundle of abelian differentials on C, in notations I was using before, this is H naught of C with coefficients in the complex numbers, right? So this is equal to degree of D minus G plus 1. And hopefully I didn't mix up the sign. Okay? So how do we use this now? Well, we're going to use this to try to estimate what happens. So let us choose a divisor D of degree 2g minus 1. Okay. Then the degree of the canonical bundle minus D. Well, the degree of the canonical bundle is the number of zeros an abelian differential can have from Euler characteristic or something. You can compute this to be 2g minus 2. So this is 2g minus 2 minus 2g minus 1. So this is minus 1. Right? So thus, this object has no sections whatsoever. Right? Because there do not exist holomorphic global functions on a Riemann surface with a prescribed 0 except 0. Right? So this means that from Riemann-Roch, we can get H naught of D is going to be equal to 2g minus 1 minus g plus 1. So let's compute. If nothing wrong happens, this should be a g. Okay? So this means that the divisor D has a g-dimensional space of sections. Okay? Then for a generic point P in C, generic means not in the base locus of this. Which is to say that not all of the sections vanish there. We will have H naught of D minus P will be H naught of D minus 1. So the dimension of the space of sections of this bundle will be 1 less because you impose one condition that it vanishes somewhere. Okay? And continuing this, and here there is something that you technically need to prove, but it's not so hard. So this means that for P1, PG generic, we expect H naught of D minus P1 minus dot 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 minus PG is equal to H naught of D minus G. And now this divisor, notice this was degree 2g minus 1, so this whole thing is in peak g minus 1, and hopefully it's generic enough. And this is 0 because H naught of D was g. Okay? So the expected dimension of the space of sections of a general divisor D in peak g minus 1 is 0, and then you can argue that on a locus of codimension 1 it can drop, it can jump to 1. Okay? I realize this is not a proof. It can be made into a proof quite easily because you just see that, let's fix all the points here, very general, except the last one. And then this system will have some base points. If you take one of them, certainly H naught will not decrease, it will remain 1. So this certainly gives you a codimension 1 thing in there, so that's a divisor, and then we can feel reasonably safe. Okay? So that's sort of a proof. The reason I wanted to do this is there will be a somewhat harder proof using Riemann-Roch shortly, and I wanted to do it. Okay? So this means that on peak g minus 1, we have a very natural, well, I think quite natural divisor. Notice that somehow this g minus 1 is 1/2 of 2g minus 2. So if you try to use this thing, you wouldn't get much information. This is in peak g minus 1, this is in peak g minus 1, so it would just tell you that generically they have the same. So let me also remark that peak g minus 1 of C has a very natural involution which takes D to Kc minus D. Right? If this is a divisor of degree g minus 1, this is degree 2g minus 2, so we get a divisor of degree g minus 1 again. But still, this peak g minus 1 doesn't have a structure of a group that I have told you about. So to have a structure of a group, I need to identify it with peak naught. And then you can ask me how on earth am I going to do that? There is a choice. And indeed there is a choice. And there is a following theorem due to Riemann, which is quite striking and which I'm not going to prove, for which I do apologize sincerely, because it requires some work that goes into the curve theory and we won't have time. This is called Riemann's theta singularity theorem. Theta singularity theorem. I should also mention the name of Kempf here, who contributed something to further making this more precise. Okay, so the version I state, I think, is due to Riemann. There is more that is due to Kempf, but I don't want to state it as a point. So the statement is as follows. So we need to identify peak g minus 1 and peak naught in some interesting way, right? So one way to construct a divisor of degree g minus 1 is to just to take a sum of g minus 1 points. So we note let sort of AJ, so this stands for Abel Jacobi, taking a curve to degree g minus 1. So you take g minus 1 copies of the curve and you map it to peak g minus 1 by taking x1 x g minus 1 to the divisor x1 plus dot 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 plus xg minus 1. That's a well-defined map. So then the theorem, there exists a vector which is traditionally denoted k, but k for algebraic geometers means the canonical, so I'll write r, which is an element in peak naught c, and this is called Riemann's constant. Such that if you take the theta divisor in peak g minus 1 of c is equal to the Abel-Jacobi image of c to the g minus 1 plus r. Right? If you take an element of peak naught and an element of peak g minus 1, you can add them, you'll get an element of peak g minus 1. And the statement essentially is that the theta divisor in peak g minus 1 is the same as the image of the g minus first metric power of the curve plus some vector that you can find. There exists a vector such as you can find. You can ask whether it's unique, it is true that it's sort of reasonably unique, and so on and so forth. Okay? That's the theorem. There is a more precise result. So this is, Kempf has contributed to this, so which is the following, that for any d in peak g minus 1 of c, you can consider the multiplicity of the theta divisor at the point d. Okay? And this is actually equal to h naught of d minus r. Okay? Hopefully I didn't mix up the sign, but if I did, I did. Okay. So this is a bit more precise because you see this is a particular case. So multiplicity being non-zero means we are on the theta divisor. And this is exactly to say that there is a section here. This is, yeah, okay. You are free to disregard this version. That's all I would want to do right now. So the bottom line here is that the Jacobian is a peak G minus 1, which I can identify with peak node. The way I identify is I choose this particular element R to do the identification. Once I have identified, the Jacobian now has a group structure coming from peak node. So if I want to add 2 points, so the group law on the Jacobian of a curve C is now going to be the following. So if you take, so I want to take xy in peak G minus 1 for, maybe I should denote them, sorry, D1, D2, right? So the two divisors of degree G minus 1. Okay? I would need to choose, so we let D1 plus D2. Well, and I need to write something of degree G minus 1. So this is of degree 2G minus 2 and minus sort of the image of 0. Under the identification of peak node and peak G minus 1. Okay. That would be the formula. Okay. Okay. So for the time being now, so I wanted to prove some statement about Jacobians now. And after all of this discussion of the Riemann theta constant and things like that, what I wanted to do is to say, to simplify the formulas, I'll mentally identify peak G minus 1 and peak node. The Riemann constant will appear whenever I need to. So when I say the image of 0, this is a little bit complicated because this is, I mean, I didn't really tell you how to identify, right? I just told you there is an element of peak node. So what you do here is you choose some point P node in the curve and you send 0 in peak node to G minus 1 times P node in peak G minus 1. Right? So this is, and it depends, yes?
In the definition of R, I think the image of the Abel-Jacobi map is just the image of the effective divisor. So then, by the definition, I don't know the possibility for R. For R is only the trivial line. Trivial line of the, I mean, the theta should be the image. Theta should be the image of the effective divisor.
So I mix something up here. So let's see. So you're saying that, of course, you're saying that this is just to say that we're taking effective divisors, right, which have sections. And you're then saying that by the, yes, okay, you're right, sorry. So when I take, cross this out mentally. So let me do it properly. So I was skipping too many steps at a time. So let me do it correctly. Sorry, you're right. I mean, I made a mistake. Okay, let me correct it. So let me be honest. So what we do is the following. So we choose a point P node on a curve arbitrarily. We'll have to do it, right? So now I want to choose a map from peak node C to peak G minus 1 of C by taking, or if you'd like, maybe it's easier to think of it the other way. So you take D and you send it to D minus G minus 1 times P node. Okay? So then the theta divisor, sort of G minus 1 here, maps to some theta divisor here. Okay? And let me say then that the multiplicity, so the theorem will be that there exists a vector, an R in peak G minus 1 of C, such that the multiplicity at D of the theta divisor as considered in degree 0 is going to be equal to the number of sections of h naught of d plus r. Okay? Sorry, I mean there was something wrong here. So the vector of Riemann's constant depends on p naught. So what I said here was the following. You take peak g minus 1. We choose by hand the way to identify it with peak naught by just taking a point on a curve arbitrarily and subtracting g minus 1 times that, so we get a divisor of degree 0. So then the divisor here, which is naturally defined as the effective divisors, gets mapped to a divisor here, which just effective divisors minus g minus 1 times p naught. But then I would like to claim that for any divisor of degree 0, the multiplicity of the theta divisor on peak naught at this divisor d of degree 0 is the same as the number of the sections of d plus r. Okay? Where r is going to depend on p naught. Okay? This is, I think now this is correct. I apologize, this was not correct. I was trying to be too smart and didn't work. Okay? I think this is a correct statement now. Does this make sense? Okay. So I wanted to try to avoid these technicalities for the time being. So I wanted to prove one statement about Jacobians, and then we'll stop for the day.
But you define the group law.
Hmm?
You have to define the group law.
Well, so the moment I have an identification of peak g minus 1 and peak 0, I have defined the group law because I have a group law here, so I'll pull it back here. So this is correct. So the group law is defined by just taking the sum and subtracting g minus 1 p naught. So that's the image of 0. The one thing you have to worry about, and which I never sort of mentioned, is that the principal polarization, if you have an abelian variety, you can choose the principal polarization, but you can translate it. It's still a principal polarization. So the principal polarization needs to be symmetric. And somehow I never verify this. Okay? And that's very important. And in general, this distinction between peak g minus 1 and peak naught is something that appears in the theory of moduli of abelian varieties. So if you want to construct the moduli of abelian varieties properly as a stack, so you should have, if you want to know whether it's a fine moduli stack, well, this means whether you will have a nice universal family. And you have sort of the analog of peak g minus 1 and the analog of peak naught. So you have the family of abelian varieties with a fixed 0. And if you have a family of abelian torsors over it, where the polarization lives. And this torsor will have an involution and the polarization. And the abelian variety will act on the torsor and will have a 0. But let's assume I never said any of these words. We won't need them.
So now, in your definition now, Jacobian, the group law on Jacobian depends on the choice of point. Are you going to?
Yes.
You are going to carry this.
Yes. So I'm going to somehow try to avoid speaking about this difficult. So there are two choices. You can either define the Jacobian as peak naught, then your theta divisor depends on the choice of point, or you can define it as peak g minus 1, and then your group law is going to depend on that. So what I'm going to do now is going to be horrible. I'll mentally confuse the two, and I'll prove something mentally confusing the two. I claim that if you unconfuse it, it will come out correct. So I'll write some formulas now, which will be made correct if you write plus r in the right places. Okay? So I wanted to prove a theorem which is known as Weld's reducibility. And I will probably be like 2 minutes over time. I apologize. And what I'll give now is actually a proof, up to the fact that you need to write r in the right places, of C, which is isomorphic to the Jacobian of C. The way you do this is you take a point P to P minus P naught. Okay? Okay? So that's a map. So now for a point P on C, for a divisor D in peak naught of C, let theta D be the set, be the translate of theta by d. So this means this is a set of points that are obtained from theta by adding d. Okay? So then the theta divisor, so this is a sub-variety of the Jacobian, intersect the theta divisor p minus q is contained in theta p minus r union theta s minus q for any points p, q, r, s in C. Okay. So notice that this thing luckily does not depend on the choice of the point p naught for identification. This does not depend, and this does not depend. So let me try to work with this in peak g minus 1. Okay. The group law I won't really need because this is an element of peak naught. I can certainly add it safely to elements of peak g minus 1. So there will be no Riemann's constant. Okay. Notice this is a very strange thing in a way. So you see this intersection here. The statement is this intersection lies in the union of these two objects. Now look at this formula for a second, and then we'll have to start looking at the formulas. The R appears here and only here. The S appears here and only here. It doesn't appear on the left-hand side at all. So it means this intersection, which is a codimension 2 object in the abelian variety, lies on such unions no matter how you perturb the R. So this is, a divisor. This is a divisor. You can perturb this divisor any way you like. But no matter what you do, this intersection will lie in here. If you were to ask, well, this intersection, it lies in the union of two things. Is there any chance it will lie in one of the two? No, there is no chance. So it sort of never happens unless you choose this to be, P. Okay? So this thing is always going to be reducible, essentially. And that's why it's called Weyl reducibility. It tells you this thing is reducible and it has components lying here and components lying here. And it's somehow a surprising thing. And if you were to try to do something like that for a general abelian variety, there is no way. And this will be the cornerstone of our characterization of Jacobians that we'll start discussing next time. So let me prove this and we'll stop. I apologize for this being taken a bit longer. So proof. And for this proof, the Jacobian of C is peak g minus 1 of C. Okay? So suppose some D lies in the left-hand side. What does this mean? Let me go here.
So just to avoid more confusion, let's erase this Jacobian statement.
Yeah, so
is Z going to fit 0? No Jacobian.
okay, so I didn't need that technically. Okay, so for a divisor in peak naught, so peak naught acts on peak g minus 1. So this means a divisor of degree 0, I can add the divisor of degree g minus 1, I'll get a divisor of degree g minus 1. I'm sorry, I shouldn't have stated this at this point. I was just trying to say that this p minus q, you can map this to peak naught, but it doesn't matter which point you choose to this step. Okay, so if D lies in the intersection of these two, what does this mean? This means h naught of D is greater than 0, and h naught of D plus p minus q is greater than 0. Okay? Well, so let's look at this. So look at h naught of D plus p. Okay? So what could happen to it? Well, it's certainly greater than 0 as well. It's bigger than this piece. So case 1, h naught of D plus p is actually at least 2. Okay? If that's at least 2, then h naught of D plus p minus whatever it was, r, there may be, by the way, so I'm translating, I should decide whether I translate forward or whether I translate backwards. So if I translate backwards, maybe the signs, all the signs here should be permuted. Okay? So then if this was at least 2, then if you impose one condition, so this means you have sections of this bundle, you're imposing on them the vanishing at R, then this is at least 1, because this is at least h naught of d plus p, and they are imposed in one condition, so this is at least 1. Okay? So in this case, this means that d is going to lie in theta p minus r. Right? By definition of what it means to translate. Okay? Case 2 is if we have h naught of d plus p is actually 1. If that's the case, you know, this is bigger than this space, this is bigger than that space. So this means then h naught of d is equal to h naught of d plus p, and maybe I should write h, capital H. So this space of sections. And this must be the same as h naught of d plus p minus q. Right? Because this space is bigger than both of this, well, bigger than or equal, and these are already of dimension at least 1. So what I want to prove then is that, so I want to prove that h naught of d plus s minus q is also at least 1 dimensional. But notice this is equal to that. So then, of course, h naught of d is also the same as h naught of d minus q. Because this is equal to that, and I didn't add anything. It's already there. And so this means h naught of d minus q is at least 1. Okay? Then, of course, so h naught of d plus s minus q is at least the same as h naught of d minus q, which is 1. So this means d, in fact, lies on theta s minus q. Okay. And this is the end of the proof. And this is, in fact, rigorous. So, I mean, if this computation makes you somewhat confused, think of it this way. I mean, if this is 1, right, all of these are one-dimensional spaces. So essentially, there is one interesting section which lies in all of this. So what does this section have to do? It has to be here, so it's not allowed to have a pole at P. In fact, it doesn't have. On the other hand, it's in here, so this means it has a 0 here. So it doesn't have a pole at P, it has a 0 at Q, so it must be in here. That's all you use. And of course, if you allow it to further have a pole somewhere at S, that's a bigger space. Okay, notice this is some very strong result. I mean, it tells you some peculiar thing about theta divisors. In general, I claim this cannot be the case, and we'll study this starting next time. I'll try to reformulate next time what this means analytically. We'll develop the analytic theory of theta functions tomorrow, and we'll see whether it fits in the theory, and then we'll eventually proceed to use this for integrable systems. I think that's it for today. Thank you for listening.